Good day, everyone. I see that the numbers have slowed down there and coming in, and I'm sure there's going to be some more that are going to trickle in as this webinar takes place. Just want to introduce myself. I'm Dwayne Hopkins. I'm the manager of the Digital Oil and Gas Initiative. This is a program co-sponsored by TechNL and Energy and Health here in Newfoundland and Labrador. Our aim of this program is to spur collaboration and innovation to deliver local digital solutions for the industry to enable the field of the future. I will host today this webinar for remote operations in oil and gas. And this is a particular perspective from a local tech company. This webinar will help build awareness, educate, and increase overall knowledge of the role and aspects of remote operations within our offshore oil and gas industry. Just to go over some housekeeping items, as this is a common webinar format, attendees' audio and video is disabled for the presentation. If you have any comments, questions, or concerns during the presentations, just include them in either the chat or the Q&A function, and I will look after them and ask them to our presenter on your behalf at the end or during the presentation. This session is being recorded and will be made available within our TechNL website in a few days. Now, prior to introducing our speaker in this remote operation webinar, I would like to first acknowledge the land of which TechNL resides. We respectfully acknowledge the land on which we gather as the ancestral homelands of the Beothuk, whose culture has now been forever erased. We also acknowledge the island of Newfoundland as the unceded traditional territory of the Beothuk and of Mi'kmaq. And we acknowledge Labrador as the traditional ancestry homelands of the Inuit and the Nunetsin, the Inuit and the Nunatsiavut, and the Inuit and the Nunatukavut. This is of which I recall home. We also recognize all First Persons who are here before us, those who live with us now, and the 7 generations to come. As First Peoples have done since time immemorial, we strive to be responsible stewards of the land and respect the cultures, ceremonies, and traditions of all who call it home. Now, for those who reside outside of Newfoundland and Labrador, I open up to you guys to respectfully acknowledge the land in which you reside within the chat function. Thank you very much. Now, I will hand it over to Karen Hocko, our TechNL Director, to introduce the speaker.
Great, and let's see. Can you please enable my video so at least they can see me?
Oh, sorry about that.
They could see, yeah. I'm in the dark.
You're in the dark.
Okay, great. Thank you so much. Good afternoon, everyone. It's a pleasure to be here. Not only am I on the TechNL Board of Directors, I'm also on the Energy NL Board of Directors. So I wear both hats today. My name is Karen Hocko. I'm with the Karen Hocko Group. I have been a consultant in both areas, both tech and the oil and gas space for 20 plus years. The theming around this webinar today was around remote operations. And I think it's important to put some context around why remote operations are a big driver for our particular marketplace. Remote operations market size is estimated to grow to $32.6 billion by 2025. The growth centers around remote operations are North America, Europe, and the Asian Pacific region. When you look at Newfoundland and Labrador and the technologies that we've developed for our harsh remote operations, it would make sense that we would actually have various interests when it comes to supporting marketplaces that are remote, potentially harsh and Arctic conditions. The areas that seem to align very well with our marketplace would be digital clean tech and operational capabilities that we've built here. Remote monitoring and data collections, for example, in natural environments, be it ocean, tidal shifts, as well as for vessels and equipment for, say, underground mining as well. Remote asset management, performing routine maintenance, virtual testing, drone technology and drone operations for long distance surveillance and site assessments and safety assessments. development of commercialization of clean and green technologies to enable remote and autonomous operations, and also performing R&D on vessels like autonomous vessels, sensors, and other emerging technologies. So lots of good reasons why remote operations should be of interest to us. So I'd like to introduce you now to our speaker today, who will be presenting on behalf of an amazing technology company that has started here from Newfoundland and Labrador, but has operations around the world, Kraken Robotics. So not only do they have the coolest graphics, they're one of the coolest companies and companies to watch in Canada today for their growth. It's a marine technology company. Kraken provides fully integrated suite of products, including batteries, sensors, towed subsea vehicles, autonomous water vehicles, and unmanned launch and recovery systems. With the 2021 acquisition of Pangeo Subsea, another super cool company from Newfoundland and Labrador, Kraken now provides subsea robotics as a service, or RAS, robotics as a service capabilities, including geophysical surveys, sonar surveys, and 3D laser inspections. Kraken's highly skilled team manages the project planning, subsea surveys, and delivers a complete data package at the end of a contract. Patrick Maranos has a master's degree in robotics and leads the underwater 3D laser inspection business at Kraken. Over to you, Patrick.
Thank you very much. Hello, everyone. Thank you for your time and interest today. I would like to apologize in advance for interruptions due to dogs and kids. I am in Rome home office and my 4-year-old has not learned to read my schedule that I posted at the office door. Hopefully she will in the next 2 to 3 years. So I'll start the presentation today, and if the connection drops, I'm not going to notice it until I reach the end. So do enjoy. Kraken is a public traded company. We are in the stock exchange. So please do not use anything that I say today as basis of your decision to buy or not buy shares, but please feel free to do so. I have split the presentation in 5 topics. We're going to do a brief introduction to Kraken and the overall product portfolio. We're going to introduce the Seavision, which is a 3D laser technology. We're going to present some results, the Seavision remote operational tools, and a remote operation example that we executed for oil and gas. So a brief introduction to Kraken. Kraken Robotics Systems Inc., with its headquarters in St. John's, Newfoundland. It's a marine technology company. Currently, we actually acquired last year Pangeo, also a Newfoundland company, and established not only a product division, but also a subsea service division. And we now provide integrated solution from sensors to fully turnkey robots. We have grown to 225 employees, which are spread all over the globe. We have offices in Canada, USA, Germany, Scotland, Denmark, and Brazil. And we deliver services and products to over 20 countries. So this is a little bit of our organogram from office perspective. We are located in Rio de Janeiro and Salvador, Boston, Bremen, Rostock, Copenhagen, and of course, St. John's, Halifax, and Toronto. One of our main and first products ever created was a synthetic aperture sonar, quite a revolution in how you do seabed survey, since it provided about 30 times the area coverage of previous technology with better resolution and quality. This product we exported to many different clients and integrated in different market AUVs for autonomous seabed survey. And we recently also launched the same capability to man-portable AUVs for quick deployments. So with a synthetic aperture sonar, you can see the seabed with acoustics in 2 by 2 centimeters resolution with included 3-dimensional bathymetry. So you have a full 3D with high precision image on the seabed. And you can acquire that level of data with that level of clarity at 4 square kilometers per hour in a survey. 10 times what usually the area coverage rate would be on previous technologies. We have developed the sensor in Newfoundland and integrated it and developed a turnkey solution for seabed survey system for mine hunting and other applications, both in offshore wind and oil and gas. So we integrated the sensor, the synthetic aperture sonar, in a tow vehicle, which is very high speed. We developed an autonomous launch recovery system and an intelligent winch. So this high-speed tow vehicle can actually operate for up to 10 knots with a 440-meter swath and over 4 square kilometers of area coverage. With the exclusive Kraken deployment intelligent winch, which is actually heave compensated with active terrain following, auto tension, auto render, and an actuated A-frame, we can install this high-speed tow vehicle into ASVs, enabling a full unmanned operation, and with about 2 times the standard operation envelope, so you can have way less weather downtime. We also produce Sea Power, which is our line of subsea batteries, which instead of oil compensated on a pressure housing, they are silicone encapsulated, doubling the current AUV endurance while still with a less weight and volume. So this is a special technology for deep waters, and we have integrated in quite a few vehicles. As with the acquisition of Penjil into the Kraken family, we also have our service business now with the acoustic corer, which is a subsea bed acoustic coring up to 40 meters of depth penetration. And it's used for foundation location on offshore wind, jackup, infrastructure decommissioning, and any geotechnical ambiguity in both oil and gas and offshore wind. We also have a 3D subsea bed synthetic aperture sonar array, which is mounted onto ROVs or also as a tow vehicle and providing a continuous 5 meters swath for also subsea bed analysis of up to 8 meters. This is usually applied to cables and pipeline burial analysis, unexplored ordnance finding, decommissioning, or general geohazards. So this is a little bit of Kraken as a perspective. And now we're going to go into the specifics of this webinar, which is a 3D laser technology developed at Kraken. So just from our perspective, Seavision is a 3D laser imaging scanner. So it's a very compact twin pod system with a laser mounted internally on a turret. Within each of these pods, there's an embedded GPU, LED light, low light cameras, the lasers, IMU. So from a software perspective, we are combining laser technology. We're combining actually edge AI on computer vision and photogrammetry. And we combine all those capabilities to enable subsea field digitalization and metrology. Seavision goes usually into any standard ROV, which is used to maintain subsea fields. It has been deployed in Newfoundland and as well in other oil fields and offshore wind, as well as research applications around the globe. In the principle of Seavision is that you have a three-dimensional reconstruction of the object that's ahead, it's in front of what you're observing. So you create a metrology accurate 3D model of your structure. Seavision is also a laser imaging solution, meaning it's not only about the 3D, but it also has a capability of generating high dynamic range photography co-registered to the point cloud. So as you can see, you have a high definition, high dynamic range image, and at the same time, you have a three-dimensional model of the structure, which allows you to measure. Seavision also operates not only with the laser technology, but also operates with the photogrammetry, enabling a self-contained visual navigation solution, allowing it to be directly attached to an ROV without the need of inertial navigation solution for the vehicle or the inertial navigation calibration. So it doesn't need a USBL, DVL, INS with a depth sensor, sound velocity probe. You can just install the sensor, take it to the field, and reconstruct in 3D. So this is an example of the Seavision being used in a profiling mode, generating the detailed three-dimensional and with a highlight on the corrosion of this mooring chain. So it's colored with given a corrosion heat map. And it all, since it's a three-dimensional model, it can be used for all the class measurements and metrology assessments. Another method of operation for Seavision is laser scanning. So since the lasers are mounted on a turret, Seavision can be used to scan what is within its field of view, and this can be done with the vehicle and the structure in motion. And then it uses its motion visual navigation for correction of this motion. So this is a 3D scan with self-reference visual navigation for motion correction. A little bit of Seavision results. This is an example of the offshore wind. It's a cable protection system. So Seavision was an ROV. It was on the manipulator of the ROV. It was pointed downwards. We did a profiling of the cable to get the cable in it quickly in its full length. But since, as any 3D perspective, you have to address the fact there are shadows, as in any cylindrical surface, you cannot see what is behind of what you're observing. You actually have to rotate around the structure and combine multiple methods of acquisition to be able to visualize everything that is of interest on your three-dimensional model. So in this example, we are combining the profiling from the top-down view perspective and with the scanning. And since the Seavision is in the manipulator, you can do all of that by simply pointing it in the direction you are of interest. This is another example on an offshore wind farm where we were contracted to measure 72 anodes. It was quite an interesting deployment since the client informed us of the anodes we should, of the anode type we should expect. And we actually detected 3 different anodes types installed on the asset, and the client was not aware that different anodes had been installed with different volumes and different corrosion rates. So there is always a little bit of a misunderstanding between what is and actually what is down there. Another example, it's a mooring chain. So it's the corrosion and metrology assessment of the mooring chain. And in this example, we're also going to analyze and show how precise is Seavision when compared to a surface 3D laser. So we performed experiments where we took a mooring chain and did a full three-dimensional model analysis of the chain underwater and of the same link on the surface on a metrology lab with the most up-to-date laser that is available on surface. So, of course, underwater at a meter distance, it is not as good as the surface, which is expected, since you're dealing with a lot of optic complexity that you do not have in the surface as marine growth, fluctuations of snow in the water column, and it is also a function of distance. But as you can see, all the critical three-dimensional structure shapes and the formations with below 1 millimeter accuracy can be modeled underwater with underwater Seavision 3D laser scanner. Now, Seavision have a few different remote operational tool sets and characteristics, which is quite important to enable a remote deployment of the system. The first perspective is, how do you control the system if you're not there? So Seavision has a web interface, meaning that I can, from any location in the world, connect to a Seavision and fully control that unit. So we have a permanent installation of a Seavision in Cove, which we could access from our office in Germany, in Brazil, and operate a system, collect data, and download data. So this is an example of the web interface, and it's just about connecting to an IP address in your network, and you have full access to the system with real-time video streaming and real-time 3D reconstruction. Seavision also has the capability of running on the edge AI solution. This is an AI solution that we are bringing to the market for mooring chain measurement. So we combine the laser, computer vision for automatic detection of links with image overlay, automatic measurement, and all the analysis. So this is really pushing everything that a computer vision can do for you into an underwater solution, which can be remotely deployed. Less interesting, but equally important, is to be able to fully control your system, not only control the data acquisition, but actually control the system itself, what is the network configuration, how it's timing, synchronized, being able to reset, clean logs, so being able to reboot the system remotely. So it's about not having physical access to your system in any way, shape, or form, and still having to operate it, reboot it, clean it. Now, since the deployment and remote deployments is not only about the data acquisition, but it's also about the plan that you made to acquire the data and the guarantees that when you go out there and you're not present, you do not have full access, how do you guarantee that you're going to achieve the results intended? So we have a full system simulation environment where we can load multiple environment conditionals, three-dimensional options to simulate the system. And interesting enough, developed was a hardware simulation. So one problem that recurrently occurred is sending the system to be integrated, not being present, and being a very complex integration because troubleshooting and something always went wrong. And the system in itself, it's a little bit of a black box. Until the system is working, it's actually not going to tell you it's not working. So we developed a hardware simulator, which allows to simulate all the characteristics of a Seavision. So you can actually test automatically if the load in the connection is enough, if the synchronization is correct, if you have communication. So we can ship that, and it has all automated testing with lights to show, oh, I am successful integrated. Now, we're going to show how we use all of that technology to do a remote operation on an oil and gas field. So in this particular example, we were contracted to do reverse engineering to enable a repair on an umbilical terminal assembly. So a cable line broke. They have no CAD models. They have no way to plan or repair the unit. So you have something which is of age. This was located in deep waters. There was no option of actually sending personnel in country. So we had really to deal with, okay, we have to solve this problem remotely. So the first thing we did was actually send out the hardware simulator to test the connection to the vehicle where the system would be deployed. So we actually detected error in the cabling between the vehicle and the system. So the laser enable was not correctly set. So if we had actually sent the system out, the laser would never have turned on. And we also detected a network configuration error. So he wouldn't even have had to be able to communicate with the system. And people would be wondering, is this system even working and on or not? The second thing we were able to do is using our environment simulation to actually simulate the principal shapes of the umbilical terminal assembly and to estimate which poses and positions, how much clearance and access did we have with the system in that environment, what would be able to be viewed and covered to reconstructed 3D. Once all of that was planned and set, we packed, shipped the system out, fully calibrated, so that once it arrived on site, it could be just plug and play. So we had, sorry for the shaky hand, this is just a cell phone video of the remote screen of the system and in operation. So we had full access and control. We have a full level of automation for multiple scans with multiple parameterization configuration that you can trigger and watch the data occur. Once the data has been acquired, it can be uploaded to the server for any post-processing and analysis. So this is an example of the multiple pieces of the data of the UTA which was collected. So all the multiple scans or multiple profiles in the different view perspective. And all of that is built together into the digital model and reverse engineer into the CAD. So this is the final result of this remote deployment. So this is a photograph, and this is the three-dimensional model, which gives you all the metrology measurements as the measurement of the entry, measurement of the tubes, measurement of all the relative distances. So this is actually not a video of the internals, but this is a three-dimensional point cloud of the internal. So it's a reconstructed 3D model. There you can see a little bit of the manipulator. So this is again a photo of the system and a reconstructed 3D model. Since it's a 3D model, you can always edit the model, like cutting out all the external of the structure to focus only on the pipeline. Measurement the distance between the broken line and the most adjacent line, so you can see any access to repair, or even reconstruct from this 3D model, reverse engineer the CAD so that you can import it and do all your planning for your repair of your structure. And now the structure is a digital structure, which means it can always be compared to any future analysis of that structure for change detection, corrosion assessment. So thank you very much for your interest and attention today. I hope this was at least instructive and not overly monotone. I'm open to questions. Thank you.
All right, thank you, Patrick. That was fantastic presentation. So I like the idea that what you're using there is sort of from that digital side of things of looking at a digital twin beforehand to basically develop your plan of attack on how you're going to do all your measurements, as well as using that in a digital twin in the future for future analysis of that system. So I'm going to put it out there for any questions or comments, and I'll see which ones are coming through. I got one here. What are the minimum network requirements to transmit data? What's your worst case?
So we like to operate in gigabit Ethernet because it means that the system is operating at full capability and it's a lot more comfortable. As you reduce the rate, the only thing the system really needs to transmit topside is a video feed, and that video feed will deprecate in quality as the connection goes down. So you can regulate what the quality of the video feed is and what's the frame rate. So let's say like that, on this particular deployment, we were in the most terrible connection possible towards a third world country on a vessel with not a proper satellite link. So it can be painful, sometimes very slow video feeds and a little bit slow to react, but you can operate it in almost no bandwidth. Just gets very exhaustive.
Excellent. So you mentioned that you have worked with your various different types of ROVs and with the Seavision here in Newfoundland. Is there any can you discuss about those projects that you've had in Newfoundland?
Well, I operated with the two major oil and gas operators in Newfoundland. We have deployed together with them, but I don't feel comfortable without the authorization discussing the specifics of the results of what has been acquired, achieved. But I can say that we have had very successful deployments and saved significant amount of, let's say, downtime and money by having the correct CAD structure identified and repair plans.
Oh, excellent. And I got one more question that's for me. I'm not sure if I missed it or not, but how effective is your laser in murky or cloudy waters? A lot of your visuals and pictures that you had was quite clear. I was just wondering, how does murky waters affect your laser?
So you're not gonna, so let's say like this, the turbidity will deprecate system quality in the results. So as the turbidity increases, you're gonna have more noise, meaning you're gonna lose a little bit of the point density on the surface because a little bit of your laser will be reflected by the marine snow, for example. So you're gonna have noise in the water column. You can remove that noise in post-processing. That's not complicated, but that still reduces a little bit of resolution. The turbidity also will reduce your operational range. So the maximum range, the light and laser penetrates the water column is given both on the laser power and the distance. So, and the more turbidity you have, the closer you have to operate to the structure. In the end, the laser survives as long as you can actually operate an ROV. So if you cannot see anything on the ROV anymore, you're not supposed to be down. You're not supposed to be there any longer, and the lasers also stopped working. But as long as you can see, you can model in 3D.
Excellent. And I got one final question coming from the audience. How long does a typical scan take?
5 seconds.
I saw that, Garrett. Yeah, mind blowing. Absolutely, that's quick. Yeah, so I haven't gotten any more questions or comments coming from, a lot of comments coming from the audience regarding great imagery. I think a lot of people are amazed by the solution that you're presenting there and how clear and precise it is. So there's a lot of comments just saying, well done. But right now, if there's no further questions or comments.
Just to complement the question, so this video is real time. This is not accelerated. So you can see the laser line passing over the structure.
Yes, excellent.
And that is a 3D scan.
And that's just one scan providing that propeller. Or
yes.
Sorry.
So that's a scan which gives your entire field of view. And you can also profile, which is continuous motion. And the continuous motion means the system's always recording as you move along. And the velocity of your motion can be as quick as you wish, so to say. We have acquired laser at, I think with the catfish at 6 to 8 knots. It's just that the resolution between the laser lines, it's 100, we're acquiring 120 laser lines per second. So the faster you go, the more distance you have between lines. It's just a very basic math, which I will not dare to do on my head online on a webinar.
But yes, I can understand that it's quite quick in general. I got one final question before we go into our concluding remarks. Coming from the audience, do you see any other applications for your technology?
Other applications. So the question I have is everything that you need and you want to have digitalized or measured, this is intended to be as common in any underwater inspection as an ROV video camera feed. I mean, it is a video camera feed. The only advantage is that you actually get a metrology and a model out of it. So it's our hope that it becomes just a standard in the market for any subsea inspection. Because if you're using a camera, there is no reason you cannot get a 3D model of it. So you're really going from a plain 2D inspection to a 3D inspection, which you can even compare in time to create a 4-dimensional analysis of your asset over time.
Wow. Thank you, Patrick. I like your point of view there. It's the way everything is becoming very sophisticated now. It's just a matter of fact, this is going to be standard practice. You're absolutely right. This is the way things are going in the digital world. So with that, I want to say thank you. And I'm going to pass it over to Karen now for any concluding remarks.
Sure, I'm going to riff a little bit on this one because this was such a good presentation. This is Commercial Conversations 101. So those of you that are developing new technologies or are part of the market, opening markets, this presentation was just top in class. And I'm going to tell you why. There's no selling here. But what is implied by this technology are the cost savings. For example, he talked about the reduced weather downtime, the application or what this means in terms of safety, less people involved. You can actually access this through a web from anywhere in the world. They talked about deep water. And so the applications, when you think about deep water, it's the Flemish Pass, it's Brazil, it's Guyana, it's the Gulf of Mexico. So this is applicable all over the world in terms of supporting offshore operations. I love how you spoke about how there was an aging asset or that didn't have any CAD drawings, which made me giggle because then you had to restart from the beginning. But the applications for aging assets offshore are significant. So this is a very fit for purpose technology coming from Newfoundland and Labrador that has application around the world. So I want to really, pardon my enthusiasm, but I was just really taken by how you were able to communicate to us and hear the story and just the tremendous opportunities that you've opened up as a result of this technology for the oil and gas industry, not only in Newfoundland and Labrador, but globally. So well done, Kraken. I'm really impressed by what you've done today in terms of educating us, not only about the technology, but also about how to talk about your technology and the applications around the world.
Yes, well said, Karen, well said. So with that, I'll bring the webinar to a close. Thanks again to Patrick and Karen for your wonderful insights. And if you want to reach out to Kraken about this technology, you can always reach them at Kraken Robotics, our services, Seavision. Thank you very much. Thank you, everyone. Cheers.
Thank you very much. Cheers, guys. Thanks for the webinar.